And then now I have to share screen here.
It's already being shared.
It's already shared. Okay, fine. So let me just go to this. Yeah, fine. Okay, so let's start. So today I'll start with one of the two main theorems in this course, the inverse function theorem. So I'll spend a bit of time explaining the context of this. But before we do that, here's a nice theorem about which is just about metric spaces. So this is like a preliminary result. This is of some interest in its own right, apart from the inverse function theorem, the contraction mapping principle. Oh, for some reason the screen is, there's a reddish. Okay, now it's okay. Yeah, fine. Contraction mapping principle. All right. So then, as I said, this is about metric spaces. The question is, if you have a function from a metric space to itself, it's a very general question which crops up in various contexts, not just mathematics, in fact, even in applications. The question of existence of fixed points. So the setup is, let XD be a metric space. Actually, the metric is not so relevant for this. I mean, you just have a set and you have a function from a set to itself. When does it have a fixed point? F from x to x. To begin with, let's just assume it's a function, no further assumptions. When does F have a fixed point? I.e., a fixed point by definition, i.e., when can we say that there exists x in x such that f of x equal to x? So as I phrased it, it's a very general question. I mean, as I said, you don't even need a metric. Whenever you have a set, you can ask this question. Now, you would have already seen this even in your class 12 or 11 or 12, an example of a theorem which states that there is a fixed point. Example, let's take a continuous function from the closed interval to itself. We know that the intermediate value theorem tells us that such a function has a fixed point. Now, in fact, this actually here I've taken 0, 1 to 0, 1, but it can be any closed interval, closed bounded interval. The same thing will hold true. Now, the analog of a closed interval in Rn is a closed ball. So one can ask, if you have a continuous function from a closed ball to itself in Rn, does it have a fixed point? And the answer turns out to be yes, but it's a non-trivial theorem in topology actually. One needs a little bit of algebraic topology to prove that. So my point in mentioning this is that this question of existence of fixed point arises in different ways, and then the proofs are also, the methods used to prove the existence of a fixed point can be very different. So as I said, for the closed ball, one has to use algebraic topology, but in our setting, it's quite easy actually. So our setting is that, so the theorem, it's quite easy. On the other hand, our assumptions are very strong. They are too strong actually. So the first assumption is okay. Let xd is not so strong. Let xd be a complete metric space. That's the first assumption. If f is a contraction i.e., if there exists c less than 1 such that distance between f of x and f of y is less than c times distance between x and y. For all xy in x. So a contraction by definition is a mapping satisfying this this property that the distance between the images is less than a constant times the distance between x and y, and it's crucial that the constant is strictly less than 1. So for instance, the identity mapping would not be a contraction. Then f has a fixed point. So this assumption that the map is a contraction is a very strong one. So that somewhat limits the use of this theorem. Unlike the previous one, where the simple calculus one, you just had a continuous function from 0, 1 to 0, 1, no further assumptions on f. Here we have to make the strong assumption, then the theorem is true. So as an example of a contraction would be f from Rn to Rn. F of x is Cx plus b, where C is some number, some real number, C in R, mod C less than 1. And B is some vector in Rn. So this would be a contraction. Now, you can check directly that, of course, that in this case, there is a, you can easily find a fixed point. This is just a linear map. It's not quite a linear map. It's what is called an affine map, affine linear map, because of the B. If B had not been there, it would be a linear map, a trivial linear map. But in any case, it has it's directly one can check that it has a fixed point. Now, so let's prove this. proof of the contraction mapping principle. The idea is quite nice. You start with any arbitrary point. Well, you don't know, of course, that this is going to be a fixed point. So what you do is you just keep on taking iterates of this. So let xn equal to f of xn minus 1, n equals 1, 2, etc. So you define a sequence in the metric space by just taking iterates of the initial point x0. So notice that this is the same as f composed with f of xn minus 2, etc. So f composed with itself. And this is n times. Then the nice thing is that this sequence, whatever point x0 you start with, will converge to the fixed point. And oh yeah, by the way, the fixed point is unique. I'll come to that. First, let's prove that the fixed point exists. So the main claim is that the sequence that we have constructed is actually a Cauchy sequence. So we can be sure that it's going to converge since the metric space is assumed to be complete. One knows that every Cauchy sequence converges. So the main thing is to show that this sequence is Cauchy. Xn is Cauchy. So to see this, let's see what the distance between. So the main point about a Cauchy sequence is that, as we know, we may not know what the limit is, but we know that terms of the sequence will get closer and closer to each other. So let's at least see that successive terms get closer, xn and xn, well, xn plus 1 and xn. So this is, by definition, f of xn, f of xn minus 1, which is less than or equal to c times, since it's a contraction mapping. Oops, here I should have put xn minus 1 less than or equal to xn xn minus 1. And one can keep on doing this. Iterate. So you start xn, you again write into as f of xn minus 1, and xn minus 1 you write as f of xn minus 2, and so on. So finally, you end up with a whole bunch of inequalities. So you'll get c to the n distance between x1 and x0. Now, knowing that successive terms are close is not good enough to say in general that the sequence will be Cauchy. But here, the successive terms xn plus 1 and xn are close by this very specific quantity c raised to n, where c is less than 1. That'll be good enough to say that it's Cauchy. So now take two numbers, m and n. Let's take an m greater than n. Then let's compare the distance between xm and xn. So repeatedly using the triangle inequality, I can write this as less than or equal to distance between, well, xn and xi and xi minus 1. Oops. Xi and xi minus 1, where I ranges from, since I've assumed that m is bigger than n, so I have to start with, well, I equals n plus 1 all the way up to m. So this is this inequality you get by just using triangle inequality several times. Now, so basically I've written it in terms of successive terms. And so I'll use the previous step to say that this is less than or equal to Cn plus Cm minus 1. Finally, and the common thing will be distance between x1 and x0. The point is, you have got what you have here is a partial sum. No, not quite a partial sum. It's the what you would get. See, we are trying to say something is Cauchy. So we are basically comparing it with the this thing geometric series. So this I will just write it as less than or equal to.
You have two
Sorry?
summations there. Shouldn't it be just one, either the series or the...
Oh, yeah. Thanks. Yeah, this, no need to write this. Yes. And here, of course, I can just take it as Cn plus Cn I can take out common plus Cm minus 1 minus n and then write this is less than or equal to. So this is 1 minus C inverse okay. So 1 minus C, the inverse of 1 minus C will have infinitely many terms. Here I've just truncated at this point C m minus 1 minus n. So I get this and we are done because C is less than 1. Since C less than 1, distance between xm and xm and xn can be made arbitrarily small if n and m are bigger than some capital N. That's I mean, I'm just going by the definition of convergent sequences. So you get this that proves it's Cauchy. Therefore, it has a limit. Therefore, since x is complete, xd is complete, xn has a limit. Let limit xn equal to x. this x is going to be our fixed point. So we just, oh, by the way, note that f is continuous. The contraction mapping, in fact, as Rudin points out, f is uniformly continuous. The contraction mapping property shows that this we have uniform continuity. Therefore, limit f of xn n going to infinity, I can take the limit inside, limit xn n going to infinity. This is going to be f of x. On the other hand, f of xn is by definition xn plus 1. So this is limit xn plus 1 n going to infinity, which is just x again. So the right hand side I have f of x, and leftmost side I have x. This proves the contraction. Oh, and also I should note that the fixed point is unique. This is easy. If f of x equal to x, and if I have two fixed points, then I use again the contraction mapping property. Distance between f of x and f of y, on the one hand, this is supposed to be distance between x and y because they're both fixed points. But this is supposed to be less than or equal to c times distance between x and y. Which is strictly less than distance between x and y, unless distance xy is 0. So actually I should not even write this less than, since c is strictly less than 1, we get distance between x and y is equal to 0. That's it. That proves that therefore there exists unique fixed point.
So which is the part that proves that f of x equals x?
Oh, that's the previous slide here. So once I know that limit xn equal to x, that xn has a limit, you just use the continuity of f to say that limit f of xn will have to be f of x here. On the other hand, you use the definition of the sequence to say that limit f of xn is the same as limit of xn plus 1.
Okay, yeah.
So that proves that it's a very nice proof, very nice and simple proof. Most fixed point theorems have very complicated. This is one, but on the other hand, as I said, the assumption is everything works out fine because the assumption is very strong that it's a contraction mapping. Now let us yeah. Now I'll come to the inverse function theorem. So some background or motivation for this is, let's start with U as usual. U is an open set in Rn. and f is a function from u to. Now this time I'm going to take the target as Rn as well. I don't know why it's okay. Target is Rn as well. So I'm going to ask two questions. Yeah, by the way, I'm also going to assume that f is C1. So remember that this means that f is differentiable everywhere and the derivative is continuous. And in one of the lectures that I posted, the last lecture, this condition is the definition of C1 is that the function from U to the space of linear transformation given by the derivative is continuous. It turns out to be equivalent to saying, more concrete interpretation of that is, it's equivalent to saying that all the partial derivatives of f exist since f is differentiable anyway, but they're also continuous functions. So whenever you see the C1 condition, just, take the easier, the more concrete one, the existence of continuous partial derivatives. Now, the two questions are, by looking at f prime, first question is, can we decide if f is 1 to 1? I'll put this. Can we decide if f is 1 to 1 if the image of f of u is open? Now, why do I care about the second one? Well, if the answer to the first question is yes, suppose I know that f is 1 to 1, and I also know that the image is open, then I can look at the inverse function. The moment a function is 1 to 1, it has an inverse. But because the image is open, the inverse function will also have a domain, will have its domain, I guess, domain of definition to be an open set. Then I can talk about the differentiability of the inverse function as well. That's one reason. So that we can talk about f inverse being differentiable. If f is just 1 to 1, f inverse is still defined, but it will be, we don't know what its domain of definition is. It's some subset of Rn. But on the other hand, if I know that the image is open, then I'm in good shape. I can talk about f inverse being differentiable. Well, that still doesn't answer why I'm again taking both to be n. Why not Rm? So here is something. Both are non-trivial remarks, one of which we'll prove. The other one, I'm not sure we'll be able to prove this. So let's remark. The first one is that if f from U to Rm, now I've taken M is C1, and if M is bigger than N, then the image of F cannot be open. So if you have a function, differentiable function from open set in some Euclidean space 2, and the target is a Euclidean space of dimension bigger than the domain, then there's no way the image can be open. The second one is if, again, same thing, f from U to Rm, C1, and this time M is strictly less than N, then F cannot be one-to-one. This part will be, the second one we'll be able to prove after I complete the proof of this implicit of this inverse function theorem. The first one, so basically what is the intuition behind these things? As I've been repeatedly saying, the main idea of using derivatives is that somehow one is approximating any arbitrary function, differentiable function, by a linear map. Now, both these statements are kind of clear if f is in fact a linear map, not approximated. Suppose f were linear. And let's look at the first statement. If you have a linear map, then why is the first statement true? Suppose I know that f from U to Rm is C1 and linear. If it is linear, of course, it's defined on the whole of Rn. But anyway, why is the image not open? Can someone tell me? Intuition. F looks like, within quotation marks, every differentiable function looks like a linear map. That is the basic idea. But this remark will help only if you can see the statement for linear maps in an easy way. So why is it clear that if we actually had a linear map, linear transformation, then the image of f cannot be open if the target has more dimension? Anyone?
I don't know how to say it exactly, but vaguely it's like if it's, for example, from 2 to 3 dimensions, then you're taking the plane to a plane in 3 dimensions, and a plane in 3 dimensions it can't be open.
That's right. That is correct. But why can't you generalize it to higher dimensions? I mean, what you said is correct, but what is preventing you from saying the same thing in higher dimensions? What can you say about the image of a linear transformation in general? Suppose I have a linear transformation.
It has at most the same dimension as the...
No. What is it? First of all, as a subset of the target, what is it? What property does it have? Forget the dimension, even before the dimension. When I have a linear transformation from one vector space to another vector space, what can I say about the image of this linear transformation? It's a subspace. That's all. The image of a linear transformation is always going to be a subspace of the target space. Then comes the remark about dimension, that the dimension of the subspace can at most be equal to the dimension of the domain vector space. That's all. That rank nullity theorem. So you will all, when F is actually linear, you will always have the image is going to be a subspace of lower dimension, and that cannot be open. What about the second one? Why is that clear that if you have from higher to lower, why can't the linear map be one-to-one? The second one. So you have a linear transformation from Rn to Rm, let's say. Why can't that be open? Why can't that be one-to-one? Where M is strictly less than N.
If it is, Can I say if it is 1-1, then I can create an inverse on the image that would be open in the origin original set. So the first remark is contradicted.
Yeah, I suppose you could say that, but yeah, that's okay. So you can say that, but there's a more straightforward way of saying that. How do you decide whether a linear transformation is one-to-one or not?
Sir, again, I'm not entirely sure if this is the correct line of thought, but what I'm thinking is you're mapping a higher number of dimensions into a lower number of dimensions. Some sort of a projection, you are going to have points that map to the same point.
Yeah, why is the question?
Right.
It's something very simple. I mean, you're supposed to know this.
Rank nullity?
Yeah, that's all. So what does the rank nullity theorem tell you?
That rank plus nullity is equal to the
yeah, but
dimension.
what does it have to do with one-to-one?
So the nullity is like non-zero, or like it's some finite dimensional. The null space is the function that goes to.
What is a null space? It is all those vectors which map to 0.
So if it's anything but the trivial.
In terms of the null space, how do you decide? Yeah, okay, let's put it like this. Let me make a general statement. A linear transformation is one-to-one if and only if
null space is trivial.
Null space is trivial. That's all. So for a linear transformation, it's very easy to check when it's going to be one-to-one. You just look at the null space kernel. And well,
sir, for some reason your screen isn't being shared anymore.
Yeah, let me share it again. Yeah, so the null space is by the way, it's perhaps good that I made this detour to linear algebra. See, unless it's a bit worrisome that your all these questions that I'm asking, you should answer almost instantaneously. Linear algebra is the foundation for pretty much everything in mathematics, but certainly this one. especially in light of this intuition that I wrote. Differentiable functions are supposed to be like linear transformations. Now, the point of this is that linear transformations are well understood. But that's an assumption I'm making. Now, if linear transformations themselves appear mysterious, then it's no point making this remark, right? So please brush up your linear algebra basics. It's apparently the question. I had assumed somehow that you are all very comfortable with linear algebra. There were just a few questions. Maybe I'll come up with some more questions and post them. It's essential that you are completely familiar with linear algebra. It should be like multiplication tables for kids. So the point is that when you are from higher dimensions to lower dimensions, the null space will be non-trivial by the rank nullity theorem, and therefore it won't be one-to-one. That's the idea. Okay, now that is one thing. So let's look at a few examples to see what kind of criterion we are looking for in terms of derivatives, which will ensure that two things. One is it's one-to-one. Second thing is that the image is an open set. So let's start with the simplest possible setting, the case n equals 1. Now here, okay, so and let's assume f is C1. The derivative exists and is continuous. What kind of condition on the derivative will ensure that this function is one-to-one? Any suggestions?
Can you repeat that?
What conditions on the derivative f prime will ensure that f is one-to-one? Here.
F dash is monotonic function.
F dash is monotonic.
F is monotonic. F dash is like always positive or always negative. Or
yeah. Right.
Or it's zero
So
at finite
actually, here the intuition is very simple. If you have a one-to-one function from an interval to R, what does its graph look like? So we have the nice option of looking at the graph of this function. If it's one-to-one, the graph cannot basically fold back like this, right? Because one-to-one just means that for every horizontal line, it should intersect the graph only once, at most once. So this folding back is not possible. So if it starts going up, it should go up. If it starts coming down, it should come down. So it should be strictly increasing or strictly decreasing. That's it. And that is ensured just by saying that f prime is not zero. Suppose f prime x is not equal to 0 for all x in AB. Then f is strictly increasing or strictly decreasing. Why? Well, simply because I've assumed f is C1. So f prime itself is a continuous function. If it's not 0, it's going to be positive everywhere or negative everywhere. Therefore, f is strictly increasing or strictly decreasing. In particular, f is one-to-one. Now, what about when can we say this map? Yeah, let's now look at the other question, the image of this map. What can we say about the image of F? So let me continue with FSC1. So I just general question. So you have a C1 function from AB to R. What can we say about the image? This also has a very concrete and simple answer, which actually this is only for the case of the real one variable functions. Anyone?
The image is connected.
The image is connected. So you can go one step further. Therefore, what will the image be?
It will be an interval.
It will be an interval. That's the main point. See, the fact that F is continuous is good enough. If F is continuous, the open interval AB is connected. Therefore, the image of that will also be connected. And we know that the only connected subsets of R are intervals. So continuity of F implies image of F is connected, which implies image is an the only connected subsets of R of the real line are intervals. Therefore, it's an interval. But I'm not quite done because it might be a closed interval, it might be half closed, be a half closed interval, and so on. I want an open interval. So just continuity will certainly not imply that it's going to be an open interval. So you can just take f of x equals x squared. The image f of r, what will it be? Well, it will be 0, infinity, which is not open. So what will ensure that the image is open? So we can just use the same condition. If f is 1 to 1 and continuous, then image f, then the image of f is open. So this I leave it to you as a homework. You can just take this. Okay. So in short, if I have this condition, therefore, if f prime is not 0 anywhere, then image f is open and f is 1 to 1. Not only that, we can say something more as well. Moreover, f inverse, what can I say about f inverse? Well, f inverse will also be differentiable. Why is this? Well, this is a one variable calculus fact. I mean, it doesn't follow from chain rule. By the way, yeah, it has to be proved separately. But it is proved in the real analysis course, one variable real analysis course, that whenever the derivative is not zero, the inverse function is also differentiable, and there's a nice formula for the inverse derivative of the inverse. So this simple-minded case of n equals 1 suggests what we have to look for. Somehow the derivative not being 0 should give us both things, 1-to-1 and the other one. But we have to be a bit careful. So let me take one more example. Let's go to R2. Now go to Euclidean space of dimension 2. Now, let me look at this function. F of xy is e to the x cos y, e to the x sin y. I'm essentially looking at, in terms of complex numbers, I'm just looking at z going to e to the z. But I'm writing it in terms of Cartesian coordinates. Now, it's obviously f is C1, since all partial derivatives exist and continuous, etc. Moreover, by the way, before I start doing the calculation, what should the analog of derivative not being 0 be in higher dimensions? We have to decide that first. The derivative, again, we can put the same condition that the derivative as a linear transformation is not the 0 transformation. That is not the right generalization. The right thing to say is that the derivative here is an invertible transformation. See here, after all, in one variable, okay, so the linear transformation is just multiplication by f prime by the usual derivative, a single number. And to say that that number is not 0 just means the linear transformation is invertible. So invertibility of the derivative as a linear transformation. Invertibility just is saying same thing as saying that f prime is a linear isomorphism, or f prime is bijective, or in terms of matrices, the determinant of f prime is not 0. However, since we have not formally defined the determinant, let's not go there. We'll do that later on. Let's just think in terms of the derivative being an isomorphism or not, or bijective. So here, if I look at the matrix of f prime, I'll get, so I'll be differentiating this e to the x cos y. No. Well, f1 of n by n, right? So x, yeah, e to the x cos y, e to the x sin y, and then the second one, no, f1. So we take f1 del f by del x, del f by del y. Yeah, this one, no, minus sign. I'll get a minus sign here. Here I'll get e to the x sine y, and then e to the x cos y. I've just taken partial derivatives of the components. Therefore, you can check directly that this matrix is invertible, or you can check 2 by 2 determinants are okay. So determinant of f prime is just e to the x, which is not 0 for all xy. So the derivative is going to be an isomorphism everywhere. But f is not 1-to-1 on R2. So, I mean, because of the trigonometric functions, the periodic in the y variable. So definitely not 1-to-1. However, one can check that f is locally 1-to-1, i.e., in a small neighborhood, in small enough neighborhoods around each point, f is 1-to-1. I leave it to you to figure out what these small enough neighborhoods are. I mean, small enough in the sense that if you think of R2, along each strip, you can divide R2 into various strips like this. On any such strip, the width of the strip will be 0 to 2 pi. On any such strip, it will be 1-to-1. So it's, I mean, small, you don't really need very small. This is infinite in one direction, in fact. But the point is that it's not 1-to-1 on whole of R2. So we have to keep this in mind, that the best we can hope for in higher dimensions is a local result, that if the derivative is invertible, then close enough to that point, it will be 1-to-1. Okay, so let me stop here. Now this lecture is very, this topic is very important. So rather than posting one more video about this, I'll continue with this live on Wednesday. So you please go over this, whatever we have done so far. Then I'll actually start the proof of the inverse function theorem. So let me end by stating the inverse function theorem. So the examples, motivating examples and counter examples that I've done should hopefully make the conditions clear for this. So let f from this time, like Rudin, I'll call the open set as E. You'll see why in a second. E is an open subset of Rn. Suppose f prime A, I forgot one crucial thing. F C1, this is very important, that the f is continuously differentiable. Suppose f prime A is invertible for some A in E. Let B, call the image of that point as B. Then there exists open U in E, V in Rn. So the picture is like this. This is your E, this is your point A, this is U. This is the point B, and this is V. B in V, such that basically when I restrict F to this U, that stuff holds 1-to-1. The first thing is that F from U to Rn is 1-to-1. The second thing is whether the image is open. F of U equals V. This answers this. Therefore, F of U is open. The third thing is F inverse from V to U is C1 as well. And just like one variable calculus, we have this formula for the derivative of the inverse, F inverse prime okay, that anyway will follow from chain rule. That the formula for F derivative will follow from chain rule. But the main point is that this F inverse is C1 as well. So these are the three main things. And so I'll continue, start with the proof on Wednesday. So let's end the meeting here now.